All right, so this video is going to go over how to draw Lewis structures. This should be pretty much a review of what you learned in first year chem. There's a few exceptions and a few new things that I'll talk about towards the end, but first let's just talk about how to draw Lewis structures. So to recall, a Lewis structure shows how valence electrons are arranged among atoms in a molecule. It reflects that central idea that stability of the compound relates to noble gas electron configuration. So we're going to be using these for drawing covalent compounds. And remember, in covalent compounds, electrons are being shared to achieve that noble gas configuration. All right, we're going to use what's called the needed available shared method. And depending upon who you had for first year chem, you may or may not have learned this. So needed is going to be the number of electrons that are needed. And by number of electrons, total. Okay. And I'll go over how to know how many electrons an atom needs. Then we're going to subtract from that the number of available electrons, which are the valence electrons in the atom. And that's going to be total for the entire compound. So total valence electrons. And that will tell us the number of electrons that are shared. And if you then take that and divide it by 2, you get the number of bonds. So it's really helpful for figuring out if there is like double or triple bonds in a molecule when you do it this method, okay? So how to figure out how many electrons an atom needs? Well, most atoms need 8. Most atoms follow the octet rule, okay? There are a few exceptions. For example, hydrogen only wants 2 electrons. Hydrogen is such a tiny atom, it can't share more than 2 electrons. So if you ever have hydrogen in a molecule, when you're counting up the number of needed electrons, for hydrogen it's always going to be 2. Anything else, it's pretty much going to be 8. There are a few other random exceptions, which I will go over in a little while. But let's go through some basic structures here. Okay. And just a reminder, if it's a single covalent bond, it's when you're sharing one pair of electrons, and a pair is 2. So this would be 2 electrons shared. A double covalent is 2 pairs or 4 electrons, and then a triple covalent is 3 pairs or 6 electrons. All right, so looking at these ones, this is on page 9. So number 12. So hydrogen, you probably already know what the structure looks like, but let me show you how the needed available shared method works. So needed, available, shared. So needed, we have 2 hydrogen atoms in this molecule, and both hydrogens need 2, so we need a total of 4. Available is the total number of valence electrons. Hydrogen has 1 valence electron, and there's 2 hydrogens, so that's a total of 2 valence electrons. 4 minus 2 is 2. And if we take that and divide it by 2, we're told we're going to make 1 bond. Okay, so again, you probably already figured out that the molecule looks like this. Okay, we use that line to signify a bond. Okay, and so we're done. Now, one thing to keep in mind is you have to use all available electrons. All right, you have to use all available electrons. It uses all available electrons to fulfill the needs of all of the atoms in the molecule. All right, so fluorine. Fluorine needed, available, shared. Needed. Each fluorine needs 8. And we have 2 fluorines. 8 plus 8 is 16. Available. Each fluorine has 7 valence electrons. So we have a total of 14 electrons available. So that means that we're going to share 2, which will again be 1 bond. But this time, instead of having only 2 available electrons like within hydrogen, we have 14 total. So we're going to start off by making the 1 bond in between the 2 fluorine atoms. So that takes care of 2 electrons. The remaining 12 go as lone pairs on the fluorine atoms. And they are lone pairs, meaning you're going to pair them up. In a complete molecule, at least at this level, you're never going to have a single electron. That's called a radical, which you'll see if you take organic chemistry, but we're not going to see any of that during this year. And then the last example, just showing you how the needed available shared method works. HF, hydrogen needs 2, fluorine needs 8, so we need a total of 10. Available, hydrogen has 1, fluorine has 7, so we have 8 available. So we're going to share 2 electrons, which would be 1 bond. We have to use all 8 electrons that are available. So let's make the 1 bond between hydrogen and fluorine. So that takes care of 2 of the 8 electrons. The remaining 6 are going to go as lone pairs on the fluorine. Hydrogen will never have lone pairs. It's not large enough to share and have lone pairs. Okay. Now let's move on to some more complex molecules. So the next one we're going to look at is NH3, or ammonia. All right, so needed, available, shared. So needed, we have nitrogen. Nitrogen needs 8, and we have 3 hydrogens. Each hydrogen needs 2, so 8 plus 6 is 14. Then we have available. Nitrogen has 5 valence electrons because it's in group 15, and each hydrogen has 1. So we have a total of 8 available electrons that we have to use in bonding. So that means we're going to share 6 electrons, which means we're going to make 3 bonds. And that makes sense because we're going to have nitrogen with 3 hydrogens. And each of those hydrogens is going to be bonded to the nitrogen with a single bond. And it doesn't matter if you arrange, you could have done a hydrogen on the top and then the left and the bottom. It doesn't really matter. And then, so we used 6 of the 8 available electrons. The remaining 2 go on the nitrogen. Okay, because another way to think about it is nitrogen needed 8 electrons. When you had just the bonds, it only had 6 electrons on it. So you have to give it 2 more as lone electrons to fulfill its need. All right, the next one, CO2. Needed. Carbon needs 8, and each oxygen needs 8. So total, 24. Available. Carbon has 4, each oxygen has 6, so that's a total of 16. So 24 minus 16 is 8. So we're going to share 8 electrons, and in order to do that, we're going to make 4 bonds. Now in this, whenever you have carbon in an atom, it's always going to be your central atom. So carbon's going to go in the center, and then we have 2 oxygens. I don't care if you do them on either side. You could have done top and bottom. Honestly, at this point, you could have done like the top and the left. I really don't care for right now, okay? We're not even talking about the shapes of these molecules yet. That's a later video. So we have 4 bonds to make. In order to make these 4 bonds, you can do one of 2 things. You can do 2 double bonds for each carbon to each oxygen. Let's finish this one out, and then I'll show you what else you could do. We need to use 16 electrons. We just used 2, 4, 6, 8. We need to use 8 more. Well, they can't go on that central carbon because that carbon already has 8 electrons around it. So the remaining 8 are going to go on the 2 oxygens. Each oxygen has 4 electrons on it, so each oxygen needs 4 more. And you can draw these lone pairs slanted like that, or you could do more within the square. It's fine. And I said that you can do something else with this. You could have done this. Oops. That is technically not wrong. That is following all of the rules. We used all 16 available electrons. We have 4 bonds. the triple bond and the single bond. Everything has 8 electrons like it's supposed to. So we fulfilled all the needs. There's actually nothing wrong with that. This is called a resonance structure, which is we're going to see in the next video. You would actually put these in brackets. This is a resonance structure. Come on, pen. And I'm pretty sure it's the next video. We're going to talk about how to evaluate, how to draw resonance structures and how to evaluate which one is the stablest configuration of those atoms, the stablest structure. Okay. All right, and then the last example here is CCl4, needed, available, shared. So needed, carbon needs 8 and each chlorine needs 8. So we need a total of 40 electrons. Available, carbon has 4 and each chlorine has 7. So 28 for the 7 plus 4 is 32. So we're going to share 8 electrons, making 4 bonds. So this one we're going to have carbon in the center again, and we're going to have 4 chlorines attached. There are the 4 bonds. Carbon's happy. It's got its 8 electrons. The remaining, we used 8. We need to use total of 32. 32 minus 8 is 24. So the remaining 24 electrons are going to go on the chlorines as lone pairs. All right, and there is CCl4. All right, so we have some exceptions, some things that don't necessarily need 8. And those include, there are some that are okay having less than 8. In addition to hydrogen, which remember that always only has 2, boron is another one that is okay having less than 8. It actually only wants 6 electrons. For example, boron trihydride, BH3, looks like this. So there's no lone pair on that boron. It's happy. It's good to go. So that's just an exception you need to remember. And then there are some atoms that will expand and have more than 8 electrons around it. Like if you look here, SF4, that sulfur has 2, 4, 6, 8, 10 electrons on it. This arsenic has 2, 4, 6, 8, 10 electrons on it as well. Some atoms can even have 12 electrons around it. So they will expand their octet. So the rule for that is if they are in the 3rd row, the 3rd period, or, and by higher I mean higher in terms of atomic number, so lower on the periodic table, 3rd period and down, they can expand their octet because they use the d orbitals for bonding. They have that 3d or 4d or 5d or whatever orbitals available for bonding. If the element's in the 2nd period, it only has the s and p. And we'll talk more about that in a couple videos about how this bonding actually occurs and what's going on with those orbitals. But for right now, let's just go through some of these exceptions. Now, actually, before I do these examples, let me go through the steps for this. So, first thing you should do is you still need to count up the, determine the number of available electrons. And that's going to be just based off of the valence. Then you're going to bond everything to the central atom, which is typically the one listed first. There are a few weird exceptions. But you're going to bond everything to the central atom with single bonds. you're going to fill your outer atoms with electrons until they all have 8, putting those lone pairs on them. And then any remaining electrons are going to go on the central atom. So only the central atom can expand its octet. The outside atoms, the ones that are connected, are never going to expand their octet. They're always going to follow the octet rule. Even if they could expand, they only expand if they are center. Okay. Now, these steps that I wrote here are only for these exceptions, the ones that are expanding or going less than their octet. You should still do the needed, available, shared, and when you get to the shared, if the number of electrons or the number of bonds doesn't make sense for how many atoms you have, that's a big hint that it's going to be an exception. And we'll see an example of that in just a little bit. We'll go through the needed, available, shared, and we'll see one where it just doesn't make any sense, and so therefore it must be an exception. Okay? So all 3 of these are exceptions, but if you're doing a problem and you're not sure, start with the needed, available, shared. Okay, that should always be your first step, and if it doesn't quite make sense, then do what I wrote here in blue. Okay, so BF3. Boron has 3 valence electrons, and each fluorine has 7. So that's a total of 24 electrons that are available. So we've determined the number of available electrons. So now we're going to bond everything to the central atom with single bonds. Boron is my central because it's listed first. So we're going to bond to fluorine with single bonds. Now we're going to fill the outer atoms with electrons till they have 8. So each of these fluorines are going to get 6 more electrons, 3 lone pairs. So they all have 8 and they're all nice and happy. And then we're going to place any remaining electrons on that central atom. But let's count how many we've used. We did 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We're done. We've used all 24 available electrons. So that molecule is done. That is the Lewis structure. Remember, boron only wants 6 electrons around it. All right, for PCl5, phosphorus has 5 valence electrons, and each chlorine has 7, so that is a total of 40 electrons available. All right, phosphorus goes in the center. We're going to bond everything to the central atom with single bonds. Well, we have 5 chlorines, so we're going to make 5 single bonds. And I'm just kind of trying to, as best as possible, evenly space those chlorines around the phosphorus. Now let's make all of my outside atoms happy, putting lone pairs on them. And now before we figure out how many need to go on the central, let's count how many we've used. Well, we used 2, 4, 6, 8, 10 for the bonding, and then 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. We've used all 40 electrons, so we're done. Phosphorus is expanding its octet. All right. And I don't want to do SF6 because I want to see one where we're actually going to have remaining electrons, and SF6 is going to look more like PCl5. Instead, let's look at XEF4. All right, so let's figure out the number of electrons that are available. Xe, this is a noble gas. Yes, this is a noble gas in a covalent compound. It is possible. Xenon and krypton are really going to be your only ones that do that. Argon maybe, but krypton and xenon are going to be the ones you're going to see. And we don't use radon because it's so radioactive, it really doesn't actually make compounds because it doesn't stick around long enough. So xenon has 8 available. And then each fluorine has 7. So that is a total of 36 electrons. All right, xenon goes in the center. And then we have 4 fluorines around it. We're going to single bond the fluorine to the xenon. Now let's make our fluorines happy, giving them a full octet. All right, so we just used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32 electrons, and we need to have 36 represented. So I have 4 more electrons that are going to be added. And we're going to place these on the central, and they go in pairs on the central atom. Forgot to mention that before, but they go on pairs. Remember, electrons will never go singly. All right, so 1, 2, 3, 4. So this xenon has 4 bonds and 2 lone pairs. That's a total of 2, 4, 6, 8, 10, 12. 12 electrons around it. That's a really expanded octet, but that's what it does. All right? So just some rules of thumb. Nope, I want to add a page. Some rules of thumb to help you insert page, blank page after current. So some rules of thumb to help you figure out how many bonds. Now, and this, actually, when I go into Let's Review, I'll talk about that. So let me just go to the next. All right, there we go. A few more examples, and then I will kind of wrap everything up. So C2H4. C2H4. Let's figure out the total number of electrons. Actually, we can do needed, available, shared for this. All right, needed. Carbon needs 8, and there's 2 of them. And each hydrogen needs 2, and there's 4 of them. So 8 times 2 is 16, plus 4 times 2 is 8. 16 plus 8 is 24. I hope I did that math right. Available, each carbon has 4, so that's a total of 8 from the carbons. And each hydrogen has 1, so that's a total of 4 from the hydrogens. 8 and 4 is 12. And then 24 minus 12 is 12. So that's a total of 6 bonds. Yes, I'm doing this right. Good. Now, in this is called, this is ethene, by the way. It's an organic molecule, ethene. Both of my carbons are going to be central here. Both of my carbons are going to be central. So I have my 2 carbons, and then my 4 hydrogens, we're going to distribute the hydrogens evenly to the 2 carbons, okay? So we're going to have, 2 hydrogens on this carbon and 2 hydrogens on this carbon. Now, hydrogen can only make single bonds. Let's go ahead and take care of those single bonds with the hydrogens. And now, so I've used 1, 2, 3, 4 of my 6 bonds. My remaining 2 bonds are going to be a double bond between the 2 carbons. And everyone's happy there. If you look at that, everyone has, both carbons have 8 electrons around it. It has 4 bonds. All the hydrogens have a single bond. So we're good. We're done. All right, HCN. HCN, needed, available, shared. So needed. Hydrogen needs 2. Carbon and nitrogen both need 8. So we need a total of 18 electrons. Available. Hydrogen has 1. Carbon has 4. Nitrogen has 5. So we have 10 available. 18 minus 10 is 8, which makes 4 bonds. Now when we draw this structure, carbon is our central atom. Hydrogen will never be central. It can never be central because it can only make a single bond. If it's in the center, that means it has to be bonding with at least 2 things, and that's impossible. So carbon will always be your central atom if it's in a molecule. So carbon, and we have hydrogen and nitrogen. I'm just going to make this in a line, okay? We have 4 bonds. How many bonds can hydrogen make? Oh, only 1. So I'm going to make my single bond between my hydrogen and my carbon. And then I need 3 more. The only other place for them to go are between the carbon and the nitrogen. Now, have I used all available electrons? We have 10 electrons we need to use. We've used 2, 4, 6, 8. Where are the remaining 2 going to go? Well, let's look to see who's not happy yet. Hydrogen's happy because it can only have 2 electrons around it. Carbon needs 8. It has 2, 4, 6, 8. So carbon's done. Nitrogen needs 8, and it only has 6 from the bonding. So the remaining 2 electrons are going to go as a lone pair on the nitrogen. 2 more examples and then we'll wrap it up. The next one I want to change from PF5 to something else because PF5 is very similar to the PCl3 or PCl5 that we did back here. So it's going to be like the exact same type of example. So let me change this to NH4+. And we'll talk about what we do with that charge because it does affect this. It doesn't affect the needed, but it affects the available. So needed will go through the same way. Nitrogen needs 8. Each hydrogen needs 2. So we need a total of 16 electrons. Available. We have 5 from the nitrogen, 1 from each hydrogen, and this plus charge means that overall we've lost 1 electron. So 5 plus 4 is 9, and then we take 1 away, 8. So we have 8 available electrons. So we're going to share 8 electrons, which is 4 bonds. And the number of bonds makes sense for the molecule because we have nitrogen with 4 hydrogens. And we've used all available 8 electrons, 2, 4, 6, 8. Now, this structure is not done. Whenever you have a polyatomic ion like this or some sort of charged compound, you're going to put brackets around it with the overall charge on the outside like that. Okay? Oh. That bell was on the video, not in wherever you're watching this. You're probably watching this at home, therefore the bell definitely wouldn't be ringing. All right, last example, I3-. Needed, available, shared. Needed. Each iodine needs 8, and we have 3 iodines, so we need a total of 24 electrons. Available. Well, this is I3-. When we had NH4+, when we had a plus charge, we took away those electrons, the number for the charge. When we have a minus charge, we're going to add electrons for whatever the charge is. So if it's -2, you would add 2 electrons, and so on and so forth. So each iodine has 7 electrons available, plus the 1 that we get from the charge, so that is a total of 22 electrons. 24 minus 22 is 2, which would mean 1 bond. But if we look, it's I3-. You can't have, so we have 3 iodines. They can't make 1 bond. So this is where doing the needed available shared gets us to a number of bonds that doesn't make sense for the compound. So, hold on. 1 bond, let me write that down. Doesn't make sense, or doesn't work. Therefore, it's an exception. Okay? So, really, for the exception, you just have to use the available electrons. Remember, we have to use all of them. Okay? So, the iodine that I have drawn here in the middle will be my central atom. And so we're going to single bond my other 2 iodines to that central. We're going to fill from the outside in. We're going to fill electrons on my outside atoms till they're both happy. So we've used 2, 4, 6, 8, 10, 12, 14, 16 electrons, and we need to use 22. So 22 minus 16 is 6. We have 6 more electrons that need to go on this molecule. And where they go are all on that central atom. So, and remember they go in pairs. So 2, 4, 6. I know, it looks weird. Probably never seen this before, but that is the structure. We have one more thing to do. Because it's a charged molecule, we put brackets around it and the overall charge on the outside. Okay. And we're going to revisit that structure in a few videos, in a couple videos, okay? So to recap, to review, carbon, nitrogen, oxygen, and fluorine will always obey the octet rule, all right? Carbon wants to make 4 bonds and 0 lone pairs. LP meaning lone pairs. So carbon will make 4 bonds and no lone pairs. You never put lone pairs on carbon. The only exceptions to that are things you're going to see if you take like organic chemistry. Okay, we're never going to see lone pairs on a carbon here. All right, nitrogen likes to make 3 bonds and have 1 lone pair. And those 3 bonds could be like a single or 1 triple bond. They could be 3 single bonds. It could be a double and a triple, but some combination of 3 bonds and 1 lone pair. That's what nitrogen likes to do. Oxygen likes to make 2 bonds and 2 lone pairs. So again, those bonds could be 2 singles or it could be a double. And this is what it likes to do. For nitrogen and oxygen, it is possible for those atoms to not do this, but this is what it prefers. And we're going to see that in the next video when we talk about formal charges. Fluorine likes to make 1 bond and have 3 lone pairs. And then just a reminder, hydrogen will make 1 bond and no lone pairs. You will never have lone pairs on that hydrogen. Right. Boron and beryllium often have fewer than 8 electrons around them in their compounds. Boron likes 6, beryllium likes 4. Second row elements never exceed the octet rule. So that's going to be like carbon, nitrogen, oxygen, and fluorine. Third row elements and heavier, so further down on the periodic table, so third row and down, often satisfy the octet rule but can exceed by using their empty valence d orbitals. And then remember, when you're writing Lewis structures for a molecule, satisfy the octet rule for the atoms first, and then if there are electrons that remain, then place them on the central atoms. Okay, so. All right, so that's it for Lewis structures. The next video is going to go more into those resonance structures which I referenced and how to evaluate which resonance structure is best.